It's okay. All right. I know I should be, but I think we're going to get started again. It's a couple minutes past 2 o'clock, so if everyone can kind of get in and get settled. And then we have 3 back-to-back, and we're going to continue kind of the same format and have all 3 folks up on the panel after the 3 talks. So without any further ado, Gina, whenever you're ready.
Is this good? Is it on? It's not on mute right now.
I think it's, I can hear, can you hear? Can you hear in the back?
Hello?
Yep.
Okay, great.
All
All right, hi everyone. My name's Gina Lee. I'm actually a summer intern at Planet, so I've only been here for about 10 weeks. But today I'll be talking about harmonizing different TOAR and SAR products using simple regression models. And I'd like to recognize all of my mentors, Arin, who talked earlier, Alan Collison, Josh Greenberg, and Ignacio. So my work this summer sort of panned out in 2 different parts. Part 1 was to first find a way to generate multi-constellation, multi-product analysis-ready datasets internally at Planet. So what this means is basically using Planet's internal tools to be able to generate an ARD stack with the different constellations like PlanetScope, RapidEye, Sentinel-2, Landsat 8, and for both surface reflectance and top-of-atmosphere reflectance. And then the second part was to then use that ARD generated from part 1 to sort of start an initial interoperability study looking to calibrate or radiometrically correct one constellation's data to another using simple regression models like random forest. So this sort of graphic is showing within the ARD, you might have Sentinel-2 and PlanetScope surface reflectance data for your localized data stack, and then hoping to potentially create this PlanetScope to Sentinel-2 harmonized surface reflectance product. So a little about why this is necessary. So this is actually a mirrored slide from Arin's talk earlier. But as many of the talks have already gone over, leveraging data from multiple satellite constellations has the potential to provide, of course, a very rich data set for time series analysis. So that graph up there is showing PlanetScope, RapidEye, Sentinel-2, and Landsat 8 across the study time period, which is just the growing season of 2017, and each dot indicating a acquisition. So sort of looking at where the crossovers are there. And then even if a satellite is able to give a precise measurement in radiance or reflectance, exact processing steps are still required before the measurements can be interoperable over different land cover types. So this lack of normalization between satellites can pose a challenge to interoperability, and the study that I'll go into for part 2 investigates one way to do this normalization. So this is just a table showing a comparison of the different satellite constellation specs, revisit rate, GSD, number of bands in the visible range, and the swath width for, again, the 4 constellations that I looked at, which is Landsat 8, Sentinel-2, PlanetScope, and RapidEye. So this is just an example of, again, why this interoperability is necessary. So here we're looking at a field within the study area that I'll talk about. And within that field, I've shown the NDVI for both PlanetScope and Landsat 8. And while they may look pretty similar, our time series graph shows us that the NDVI value across time is still slightly different. So this is just a RSR comparison for PlanetScope and Sentinel-2. As many speakers have already said, we notice the broad width of PlanetScope sort of overlaps with the BGRN channels for Sentinel-2, and then comparison of RapidEye, and then Landsat 8. So this approach that I'll go into about the study is a local analysis of a stack of data. So a more local analysis can yield a correction that reduces the variance between 2 data sets. So per pixel differences will be reduced. However, this type of correction will have limited applicability across different land covers. So basically using something like random forest, utilizing all the available bands to essentially overfit the scene. That's sort of one of the drawbacks here. So sort of to backtrack, going back to part 1 for generating a multi-constellation ARD internally at Planet, I'm going to talk about that for a little bit. So here we have in AOI about 25 square kilometers within Imperial Valley, California, which is a mostly homogeneous AOI made up of sort of desert irrigated agricultural parcels. So internally at Planet, you can sort of request orthotiles for the different constellations, Dove, Sentinel-2, Lancet-8, Rapid-Eye, giving an AOI, area of interest, and a time of interest, a TOI. So this is an example from July 10th. It returns these 4 orthotiles, which covers my area of interest. So sort of 2 passovers on this given day with the sort of areas that were imaged. And then this is what we get for Sentinel-2, Lancet-8, and Rapid-Eye. So the first thing I did was sort of create a Python module that will, so it's kind of a lot going on here, but essentially, given an AOI, to stitch those 2 orthotiles together and then crop it to that AOI that I've requested for a given time range too. So basically this module will take in a single search parameter with the AOI, TOI, the list of products like surface reflectance, top atmosphere reflectance, and then the constellation list, and then kick it off on the parallel compute system and basically return a big stack of data that gets put into a storage bucket. So it's just my AOI with all the different constellations and products for a time period. So this is sort of a visual of what that stack would look like. So this is illustrating within that bucket all the images, and then you can kind of see like where the crossovers are as well. Okay, so moving on to the small scale local study. So again, now using the stack that's been generated, the idea was hopefully to be able to use random forest to correct, say, Rapid-Eye to PlanetScope, PlanetScope to Rapid-Eye consistent values, and do the same for Lancet and Sentinel-2. So the study timeframe, again, was growing season 2017, looking at these 4 different constellations within Imperial Valley. And then the correction type was a per band random forest regression, and the type of data for the analysis was looking at just surface reflectance. So again, this is a study region, about 25 square kilometer region. So the way I built the model for each of the 4 bands was basically, so this is an example from PlanetScope to Lancet-8 consistent values. Basically take all the crossovers. So here we have 4 here that we trained on, basically used pseudo-invariant pixels to do the training, and then predict on one of the scenes, one of the crossovers that was not part of the initial training data set. And then, so now to talk about sort of the results of the PlanetScope surface reflectance corrected to Sentinel-2 surface reflectance. So this was sort of the before and the after. There's not too much of a visual difference. There were some slight differences in the R-squared and also the slopes. But same here with PlanetScope to Rapid-Eye. This was before the correction and after. And then also PlanetScope to Lancet-8, before and after. So to do sort of quick validation, we looked at a single field within the AOI. And within this field, basically what we're seeing on the left is the Sentinel-2 NDVI versus the PlanetScope NDVI with no correction. And then on the right, it's the Sentinel-2 NDVI versus the PlanetScope NDVI with the bands corrected using the random forest model. So there's a slight correction there. Looks like it's a little closer to the 1-to-1 line with slightly better R-squared. This is an example of field 2, seeing sort of similar results, not the best, but looks like the line of best fit is also closer to the 1-to-1 line there in the corrected version. And then for field 3, this one was kind of interesting. This one was very uniformly homogeneous field. So you'll notice that the dynamic range is super small in this example. But yeah, again, this one I guess didn't see a whole lot of change. Yeah, and to move on to conclusions, I guess the biggest takeaway is just 2 bullet points here. One, we sort of have this capability of producing multi-constellation, multi-product ARDs at Planet internally, and this can also serve as a framework for our external API, which is capable of retrieving and doing the same searches for specific orthotiles given an AOI and TOI. And then also this initial study that I've begun looking at local correction with random forest regression seems to be somewhat promising and can be improved in the future. That's it. Thank you.
Thank you, Gina. And next up is Peter. I think, do you want to speak? All right. That's not you? Oh.
Yeah, that's me.
Okay.
All right. Yeah, that one. She tells John. Yeah. All right. Tell him Karen reviews it. On an HDMI port and. Okay, cool. That's me. Hi. I'm Peter Scarth. I'm from a group called the Joint Remote Sensing Research Program. So we kind of got set up a few years ago out of the collaboration of a number of state government agencies who were doing similar work, I guess, along the east coast of Australia. And we kind of realised we had a...
Is your mic muted?
Oh, push button here?
You slide it to...
No, touch anything. I can talk loudly, but
There
there
you
we go.
go.
Cool,
Try that.
that's me. A collaboration of state government departments. So it's kind of like this nice collaboration between universities and government and sort of increasing the industry, I guess, that really work on policy-related questions. And that's, I guess, what I'm going to be talking about here is how can you get data that's ready for, analysis ready for policy decisions, I guess. And I spend a lot of time in the field, and so this is kind of the environment that I try and map and model is these sort of savanna environments across Australia. But I'll start with these guys, because I think the US has given us some wonderful things: good IPA, a free Landsat archive, and South Park. And there's always a South Park analogy for everything, and I really particularly like the underpants gnomes because they went around hassling Tweak and stealing his underpants at night. And when they finally got cornered, stealing his underpants, so he didn't know where his underpants were going, he got his underpants. And they said, look, we're selling them. And they went, what are you going to do? And he said, we've got this plan. We're going to collect underpants, and then we're going to profit. And I thought, bingo, that's it. So we're going to produce ARD, and then we're going to profit. But really what I want to talk about here is phase 2 in this business plan. So how do you get from analysis-ready data to something that can be used at the end? It's really drawing a long bow, but it's late in the afternoon. Okay, so So we started back in 1999. We were really lucky. We got a lot of money to map woody change. It was quite political. And it was lucky then because we were paying $5,000 for a Landsat scene and we had to buy 89 of them every year. And so they were really carefully selected. So we'd go to acres back then. And the thing is that back then, really our analysis-ready data for woody change was just cloud-free images. We'd pour over the catalogue. Ooh, I want that one. And we'd get a nice cloud-free scene for 1 year and we'd get it for the next year. And we do stuff like this. So we do change detection. And so here, you've got an image from 1 year and then you've got, roughly the same date, anniversary the year after. Apply some sort of classification algorithm over the top of that and map the amount of change. And that went into a lot of reports and it produced a lot of stats, I guess, over time, which you can see here. There are a lot of reports. We've got a lot of imagery. When the archive became available for free, it saved us a lot of money. I think by the end it was down to $1,000 a scene, so it was only costing us 90 grand a year for imagery, but zero is better than 90. And so we sort of mapped all this stuff, and that was cool for a while, and that's sort of what we did. We did sort of mapping, vegetation change, and all this change data actually for Landsat is available online, so it's like a mine for machine learning if anyone wants to get into it. Labeled image data sets of clearing. Anyway, but sort of from 2008 on, we kind of pivoted. The group grew a bit bigger, and there was a lot of policy pressure coming in from the Great Barrier Reef, from land degradation, from tree cover and all those sorts of things. And we kind of realised that, look, we've got this problem. We've got to separate management from climate, and we need to sort of build a processing chain that can handle all these multiple users. And so we built a thing, everyone built a thing. We had a thing where, TOA comes in at the top of basically Landsat, nowadays Sentinel as well, a few other providers sort of trickle in here and there. And we correct it, we do car shadow, terrain, F mask, water mask, convert it to N-bar, terrain corrected. And then we built these sort of biophysical products off the other end. So you're not really supposed to see anything here, but down the bottom we've sort of got products that come out. So we've got all these layers at the top, which are really our base data sets, and then we do burnt area, we do wooded probability of clearing, fractional cover, which I'll talk about, a whole lot of grazing land management products, and woody cover. So, but the starting point here is really, geometrically registered at this point, Sentinel-2 and Landsat, terrain corrected, with as much of the ugly stuff removed as you can this particular year. Algorithms get better all the time, we're getting better cloud masking, things like that. The horrible scatter plots, because we've seen lots of scatter plots, probably not as horrible as this, is sort of like, hey, we're trying Sen2 core over here, it didn't work, so we went to the same process with our Landsat, and so we're pretty happy that Sentinel-2 and Landsat are on the same baseline. Okay, so here's kind of where we're starting from. It's our Sentinel data. We kind of mosaic these up into seasonal composites a lot of the time for various applications, because there's a lot of cloud, and so if you can sort of mosaic them up, you can, build these seasonal mosaics. Here's me loading one into QGIS over the web. It's kind of cool. You can load an 81 gig file straight into QGIS over the web, and it just sort of streams really nicely, thanks to the magic of overlays and things like that. But okay, so we've got our imagery. That's kind of cool. I've sort of glossed over that, but everyone's talked about that all day. But for the stuff that we do, our analysis-ready data is for what we call fractional cover. Okay, so it's the proportion of green, non-green, and bare ground in any given pixel. Okay, so how do we do that? We actually collect a lot of field data then to get to this point. So there's been a large collaboration in Australia with various government agencies. There's a lot of dots on that map. There's 3,500 dots, in fact, where someone's gone out and done sort of roughly what people are doing in the animation. They've walked along and looked at whether there was a leaf above them and whether there was, bare ground on the ground, and had done that 300 times. And each one of those sites costs us about $1,000. So it's a reasonable investment, $3.5 million in a field data set to calibrate this, but it means that it's pretty good. We haven't got great coverage over in the west of Australia, but the Northern Territory guys in the middle, they've been competing with us, and they've got more points than us now in Queensland, but we'll catch up at some point. But the sites have sort of got to be, I'll sort of like this GIF, but the sites have got to be sort of set up so that they're big enough. We make them about a hectare, and that kind of covers a range of different spatial arrangements of land cover types. So, you can get cropping or trees that can be uniform or clumped and those sorts of things. And so we sort of try and characterise as much of that as possible. And then we process that. So at the moment we do an unmixing approach. We do basically a non-negative least squares unmixing in a subspace. So we map the data into a space where we can get the least amount of noise and unmix in that. We're moving sort of more towards a machine learning model now that we've got so much data to live with. And we get these images, you saw that earlier one, that look a bit like this. So here, I'm so used to seeing these, but the amount of red in a pixel is the amount of bare ground, the amount of green is the amount of green vegetation, the amount of blue is dry vegetation. So you can see, around this mountainous area here in the middle, which there's a mouse. This area here, there's a range, there's lots of trees. Over here we've got sort of kenopod shrublands, fair bit of bare ground, and over here there's a lot of dry grass and cropping areas. And so that's sort of mapped the Landsat or the Sentinel into this biophysical space. And we mosaic these up and just chuck them online as well. And the thing is, when you've got a biophysical product, it gives you the same mean across different pixel size. So, cover can scale linearly. You can get the mean of cover within a Landsat pixel of the planet underneath, and you should get the same answer. Whereas you can't with NDVI because it's not a proportion. And so here, we've got MODIS pixels sort of tilted at some funny integerized sinusoidal warpy thing up the side. Landsat, Sentinel, and Planet, all sort of showing the same information. Landsat, MODIS, Landsat, and Sentinel, of course, the algorithm just runs on the spectral bands. Planet doesn't have enough, but the magic of regression, we can, just regress locally, and it does seem to work. So it's really interesting hearing about that. But at the moment, the government's gone, trees. And so the really important thing is tree cover at the moment. We want to know where our trees are. And typically, with our time series, we do that by looking at the amount of green signal. So we've got this green biophysical signal, and we can look at that and how that changes over time. So this top graph here for this very sparse shrubland, it's not a northern hemisphere boreal forest, it's this scrappy acacia stuff. This is the green signal. We basically fit a spline to the base of that over time and use that as the estimate of the amount of woody vegetation that's there, because generally the grass will grow and then it senesces off, and the lowest point of the time series is generally the woody vegetation. And you get something that looks like that. So here you can see that forested area in the middle is now well represented as trees, and everything else is sort of grasslands around the outside. We can apply a function to that and get biomass. I won't go into that. But we want for our grazing products non-woody cover as well. So we've got the trees, we want the grasslands as well, and the grass is generally underneath the trees. And so to get rid of that, we've got a time series of a time series. The processing starts becoming interesting, I guess, but it's a really important variable for grazing and reef. And so to get under the trees, of course, we've got an estimate of the amount of green vegetation. We use a machine learning model to get an estimate of the amount of persistent non-green vegetation. So there's a whole canopy structure there that we need to account for. And generally that's kind of characterised reasonably well. And so we can go, for example, the darker coloured lines are what we get after the correction. And the like cyan and yellows and purples are kind of the amount of that variable. So in this case, non-green, green and bare ground before a correction. So we're pretty confident that we can correct under a reasonably dense tree cover to get the grass cover underneath. And so we get a defoliated product at the other end. And that's sort of what we give out to people in the grazing space. And we can do time series stuff on that, like look at maximum ground cover for productivity of grasslands and what have you. But okay, we've got all these things, but we really want to get them out to people. We can do reports and stuff for policy, but unless it's accessible and discoverable and interoperable, all the buzzwords we've got here, it's not really much use. So because we chuck everything online as national mosaics of cloud-optimized geotiffs, you can do a notebook. Everyone loves notebooks, so I did that horrible mosaic there the other day, just as the highest level of overviews on my Chromebook, my daughter's Chromebook. And it's kind of nice because the entire national data set, I can zoom in anywhere and do stuff, which I've got over here. So it's an example of coal seam gas, someone doing a plot of woody vegetation increasing, those sorts of things. So you can experiment, analysts can experiment with the data, use it for teaching at universities and stuff like that. It's kind of cool. The other thing is through APIs. So we've got a number of APIs that do time series drills through these data sets back through the full Landsat archive. And they're kind of scale invariant as well. So you can drill all of Australia or a paddock, I guess, and it returns in the same time because you just act on the pyramids. And so, we provide tools that can give you a time series like what you see at the bottom there. We can sort of do custom clip and web processing services. And we're sort of working at the moment on there it is, like a land cover prediction API. So because you can get the time series back pretty quickly, you can run tools like, Python auto forecast and other machine learning economic models against a background of, we use, rainfall, lagged accumulated rainfall, Pacific decadal oscillation, tripole oscillation index, a whole lot of these climate variables. You can start to build a model that will predict the cover of the season ahead, and that's kind of valuable to see in here where things are different, and also to sort of predict going forward in the future what your grassland is going to look like. That's the tech end. At the other end, there's sort of people that are using that to build front ends. So this is Veg Machine. It's just a government-y portal, I guess, that we sort of snuck up outside the government system, so it was really cheap to build. And it allows you to sort of go anywhere in Australia and draw a polygon, pull the time series. Here we're just comparing two paddocks with different management strategies. This one here is grazed a bit heavier. You can look at the imagery and all the products up here, or you can extract a time series and go, that paddock there's got a lot more bare ground compared to the other one. It's got the same rainfall regime, it's been grazed heavier, those sorts of things. And they're really useful for basically building a dialogue, building a story with landholders, and using it to see, these parts of the paddock are being used more heavily than others, and what have you. But it's still not what a lot of people want, and I think we heard this yesterday. Like, we've got all this imagery. You've got a map here, for example, of total standing dry matter, the amount of grass biomass that can be eaten. Woo, that's cool. I love that. But people on the land don't get it. So you get watering points, because the cows only graze within 3 k's. These are big polygons. So this is a paddock. That's 3 kilometres, what's that, 1.5 miles or something across. So that's how far a cow will graze from a watering point. And so these are the grazed area of the paddocks, and you can sort of intersect them here and work out what's going on. But people still don't really want that. They want a printout of an Excel spreadsheet, which tells them, the tons of feed that are in their paddock. And that's the level of information that we sort of got to get to. We do all this work and then you hand them an Excel spreadsheet. But that's kind of delivering what the user wants. And kind of getting close to finishing off, I guess the ultimate test for analysis ready or analytics ready information is that it's getting used. So we're seeing sort of increasing use of the data. We see media reports of, turning data into a profit. That's what you want to see. I love seeing people, I love going to field days and people stand around and look at imagery and then try and make sense of it and interpret the landscape in their ways. And we also get, we get our, we've been mapping land clearing for a long time, and a lot of the industry don't like us mapping land clearing. It's kind of big brother, but they're kind of on side. So we get headlines like this, invest in science to reveal full picture on vegetation management, because we've managed to explain to them that we map land clearing, we don't map regrowth, and they've gone, oh geez, all right, and they'll lobby the government, and they've just got us, a couple of $1 million to start mapping regrowth. And I think that's really nice that you can have a program that gets to that point of working with users that, even though they don't like what you're doing, they know that the science is important and they'll help, they'll go into bat for you basically to get you more funding. So in summary, we all collect a lot of underpants in our lives. Collecting underpants is really cool, and put your underpants on Git, because I think you really, there's lots of little experiments that you do, it's like, oh, this is a cool thing. I do it all the time, I'm terrible. I get distracted. And I think it's, it's really just trying a few things, iterating those with users. I think that's my basic point. Start with a few underpants and iterate with users. So when you're going through phase 2, I find just try and do the simplest thing possible, get it out there. They'll go, oh, that's shit, I want something better. And you sort of iterate pretty quickly. And really just getting as close as possible to user requirements and no further. So there's nothing worse than over-processing data to the point where you're kind of adding noise to it over and above what you sort of want at the other end. The tricks are we're still iterating, we're still working with users all the time to work out what people want in remote sensing data from government. And the challenges, the last one I guess I'm thinking about now is remote sensing is great. We've got these lovely raster data structures. They're great. But trying to integrate these with less formal data structures like social science data and those sorts of things are going to be a challenge. But I think that's kind of the interoperability we need to look at down the line, is how we can, how we can use these data, to give an example that I'm working on at the moment, to look at mental health issues in various parts of Australia that are related to vegetation cover, for example, and that's posing some interesting interoperability questions. All right, I'll stop there.
Awesome, thank you very much. I missed the first part about the underpants, so I'm going to have to go back and review the tape. I think Scott is ready.
Okay, is the mic on? Does that sound right? I guess so.
I can hear it. We
Let's see if this works.
may have to do what I just did a second.
Come on, there we go.
Oh, there you go.
All right. So now for something totally different. And can I, is it okay if I don't stand there?
No, yeah, I think.
I have to stand right here?
Well, because we have lighting and we're taking, and if you go there, exposure time is too short.
I somehow feel like more of a giant standing here. So it's just a little, it's a little troubling, but okay. So I guess I'll just stand here. I don't really like to walk around. So my name is Scott Arko. I'm the Deputy Director of the Alaska Satellite Facility at the University of Alaska Fairbanks. And I didn't know I'd be the only person talking about radar, but that's great. I'm happy to do so. We're an archive operator, so I guess I'm a collector of underpants, one might argue. But we're not trying to sell your underpants. We're trying to make your underpants better. I don't know if that's a good analogy to go with or not. So I decided to start off, because I was afraid that I was going to lose everybody when I said the word radar, that I start with a couple of kind of eye candy things. So the image in the upper right-hand corner is actually Laos Saddle Dam D. So a few days ago, or about a week and a half ago, Saddle Dam D failed and discharged an entire reservoir through a series of villages in Laos. And it killed 36 people, I think, at this point, and displaced thousands. And this is, while it's interesting to see the discharge of the reservoir, the point that I wanted to make is that a year ago, 2 years ago, 3 years ago, just that little time series sequence right there from radar data would have been really hard to make. Now I made this this morning while I was sitting in the back, and so things are getting better, and that's what we're heading toward, hopefully. The image in the lower right doesn't look like a radar image. It's actually an INSAR time series of Sierra Negra in the Galapagos Islands. And what you're seeing there is about a half a meter of inflation in Sierra Negra over the course of 6 months or so, preceding a relatively minor eruption of that volcano. So who are we? I'm the Deputy Director of the ASF DAAC at the University of Alaska. We're a distributor. We're one of NASA's distributed active archive centers. We're the center that specializes in SAR data. We currently have an archive of about 6 petabytes or so that's on spinning disk, available for people to download free of charge. If you'd like to come download some of our data, go to our client there, and you can sign up for a free account, and you can get access to anything in our archive that you would like. Or you can use our API. We have a very nice RESTful API that you can use to search, you can use to download, you can use to do whatever you'd like. 6 petabytes seems like a lot. Somebody yesterday said it would take 6 backpacks, I guess, because you can put a petabyte in a backpack now, but that seems like, 10 years ago that would have been unthinkable to me. In 3 years, we're going to be supporting a mission that's going to collect a petabyte of data every 10 days. So over the course of the mission, the lifetime of the mission, it'll collect 150 petabytes of data if it goes for 3 years. If it goes for longer than that, it'll collect more. So we've got a big problem on our hand that we're trying to get a handle on, and ARDs kind of play into that role, or into that problem. This is just a little map of the distributed active archive centers. If you've used MODIS data or Landsat data or ASTER data or whatever, you've probably gotten data potentially from a NASA DAAC. So I didn't know if I needed to go through this or not, but I thought I quick would. A little bit about radar. So what we've been seeing for the past couple of days is down here in the optical and infrared signals part of the spectrum and part of the atmosphere. We operate in the centimeter, the millimeter centimeter wave range. Well, one of the nice things is the atmosphere is really clear. You know, you hear no clouds in radar, right? Well, I'll show you an image later that has some clouds in it. But you know, in general, the atmosphere is very clear and allows us to collect a lot of data, hopefully, and collect regular data now. So we have 24/7 imaging capability, can image in the night, day or night, all weather. Because we provide the illumination source as well as the reception source, tends to be a very stable signal over time in general. And you know, what I would like to show, or what I hope, is that it's complementary to all the systems that you all are using. So all of this is just one more layer in a workflow, or this is one more layer, hopefully, that you could mix with your optical data. At the wavelengths that we operate at, radar scattering is really pretty physical. You can think about it as bouncing off of objects. You can think of it as bouncing off of the ground. You have different types of rough surface scattering. You can think of double bouncing off of things like trees, volumetric scattering inside of trees, or you know, double bouncing, things like that in urban signals. And this, you know, in general, works pretty well, plays into the change in polarization, the change in scattering associated with polarizations. The other thing we talk about is phase. And so if you're familiar with electromagnetic waves, this is an electromagnetic wave. So we have full, sorry, I'm going to zip through this here. So we have full periods of the wave that we receive back at the sensor. And then we have that little bit at the end. And that little bit at the end is what you hear referred to as the radar phase. And that's really the important part. All of the stuff before that, all of those full cycles don't really matter. What matters is that little bit at the end. We measure that phase, and we can measure differential phase to measure very, very slight changes in the Earth's surface. And that's what's important. Or that's one of the things that's important. I think everybody knows about Sentinel-1, so I'll probably just skip over this. But 6-day collections, or 6-day repeats right now between the spacecraft. INSAR is possible between the spacecraft. Works great, actually. Large swath width. This is, from my perspective and many people's perspective, we're kind of entering the golden age of SAR right now, which is great. So this is another example just to kind of get people's attention, hopefully. So this, courtesy of Google Earth on the right-hand side, is somewhere in New Mexico. I can't even really tell you where. It's somewhere in northeast New Mexico, where they're doing oil and gas extraction. And so they use hydraulic fracturing, and they're pulling out minerals, or pulling out gas and oil here. And if you just look at an optical image, you can't tell what's happening. So if I look at a differential INSAR time series, I can tell exactly what's happening. So I can see which wells are active. You can actually see which wells are causing distortions of the Earth's surface over, this actually isn't that long of a time period. This is about a year's worth of subsidence in that area. But it's the power. I mean, this is kind of, I feel like maybe I'm preaching the choir, maybe I'm not. But this is one of the things that I think is remarkable about SAR, is that we're able to measure centimeters of distortion in the Earth's surface from 700 kilometers away, which is remarkable. So why is analysis-ready data important for SAR? So SAR has suffered, I think, in the past from a lot of issues. One, we've used obscure data formats, things that have been impossible perhaps to use, under the notion, and I won't say where this comes from, but under the notion is, well, if people can't figure it out, then they shouldn't be using the data set. That's the wrong attitude to have. It can be difficult to interpret. Radar geometries are not normal geometries that we think in. Tools historically were expensive, hard to get, and hard to use. The data were historically very expensive. Thousands of dollars per scene, perhaps. And we didn't have any really deep global time series. No, there's no Landsat of SAR. The closest is the European Space Agency's ERS and NVSAT series that collected large areas and collected deep time series, but it's still not quite, I think, a Landsat of SAR. But in keeping with the musical reference from this morning, the times they are a-changing, in fact. Things are totally different now, or they're getting there at least. And we see this in our user community. So historically, we've serviced many tens to maybe some small number of hundreds of users over the course of our most of the history of our data center. But that little tick you see in the middle is when the Japanese Aerospace Exploration Agency allowed us to start offering their pulsar, their ALICE pulsar data, free of charge without restriction. And somewhere in there is Sentinel as well, when we started mirroring the Sentinel archive. But you can see we've gone from a few hundred active users perhaps to now having 8,000-10,000 active users per month. And these are people that are downloading data, coming and getting data from us, and hopefully using that data. And we'd like to make it easier for them to use. And so what we're heading toward is what we consider to be kind of foundational products or analysis-ready data products. And these are radiometrically train corrected. I don't know why we have to call it that. It's really an orthorectified and radiometrically corrected image. Has the noise removed, is calibrated, so now we can look at a time series, and that time series means the same thing across many, many steps. We correct the geolocation, we correct the radiometry, and we provide mask information. So we provide quality information telling you where the data are no good, where you shouldn't use them, where you can and where you can't use them. Based on that RTC product, we have a couple of different change detection products that we're developing, and then interferometric SAR images, or interferometric SAR products. So differential interferograms, correcting for topographic phase, correcting for atmospheric phase delay. And these are all relatively complicated things to do to some extent. And so we want to take all of that work out of it from the user side and give the user something that they can use directly in their application, hopefully. And then we want to export them to cloud-optimized geotips and standard coordinate systems, get rid of the range azimuth radar coordinate systems. You should never see an image. If you're just working with the data directly, you should never see an image or a product in range azimuth. So what does RTC look like for us? This is somewhere in Western Oregon, or Western Arkansas, excuse me. That's just an optical image. This is a correction factor based on the SRTM DEM. This is the original radar image here, a colorized version, so it's a band ratio image from Sentinel. And then once we correct it, what you can see is a lot of the topographic effects go away. So a lot of the brightening on the near side, the darkening on the far side. We also correct for geolocation. And this is now a product that somebody could actually use where you can say, oh, I can make a measurement from this product and understand what it means. And that's where we're heading on a grand scale, hopefully. The time series is getting much deeper now. This is something that I generated a few weeks ago for the Arctic Basin. This, of course, is something that we're very interested in, is the Arctic. And the question was, where do we have at least 10 collections per month? So you can see over time, and originally it was, or in the initial part of the mission, it was just focused on the Eastern Arctic. But over time, the Western Arctic will fill in to the point where now most of the Arctic Ocean, most of the Arctic landmass is being imaged at least once every 3 days, and many areas are being imaged much more than that. That's an amazingly dense time series, and for SAR at least. I mean, I think that's really quite phenomenal. And it allows us to do things that we could never have done before. Let's see if this will play. So this is the Nares Strait in northern, off of Ellesmere Island in Canada, between Ellesmere Island and Greenland. And these are daily composites from Sentinel-1. And so now we can take these data and couple these data with computer vision algorithms, and we can actually measure surface currents and the change in surface currents on a daily basis. Something that would never have been possible before. The best you could do was maybe launch a buoy in there. It might stay for a few days, might stay for a few months, you don't know. But the great thing is here you can see the land isn't moving. The ice is very much moving, in fact. And it varies greatly over time. The ice moves back and forth, the currents change. This is all kind of fueled by the Beaufort Gyre in the Western Arctic Ocean. This would have been very hard with traditional EO imaging. This is a pretty cloudy area for the most part. But now we're able to start generating these types of time series in the Arctic. And it really isn't just the Arctic. Oops. Maybe. there, oops. If we look at the whole planet, this is the archive effectively at this point in time for the entire planet. You can see many areas have been imaged thousands of times, but for the most part, every landmass on Earth has been imaged hundreds of times at this point, allowing us to get this kind of deeper time series. So the way that we do this is through something we call HYPE, or many people call HYPE 3. You can go either way, I really don't care. The URL is right there. This actually started off as an undergraduate project. I had 3 undergraduate students working for me a couple of summers ago, and the idea was to create a cloud-based processing system where we could throw in algorithms, we could throw in anything, we could throw in some SAR data, and it would process automatically in the Amazon cloud. And it really, it works. It works great, in fact. Right now, the way the system works now is you can have even either a human interface, so we have a GUI that you can access, or there's a Python machine-to-machine interface that you can go in, you can place an order, request a region to be processed to a certain level. It goes through, kicks those jobs out into AWS, processes the data, and then provides the data back. As a data provider, it's actually cheaper for me to process the data and give you that little piece of data that you want than for you to come in and download a bunch of data from us. If you come in and download a bunch of data, we have to pay egress fees on that. If you come in and get just a little piece of data that you wanted maybe, rather than a full scene, it probably saves us money in the long run. And so this is something that we're looking at kind of across the spectrum for a variety of different types of processing. So we currently offer RTC processing, full frame or region of interest. We offer INSAR processing. We have change detection algorithms right now that are being used for things like surface water detection. Offer a variety of resolutions. And it's all fully automated, which is the great thing about it. If you come in and place an order, it goes out, spawns out some EC2 instances, processes the data, puts the data into a bucket. You can come get the data, kills the EC2 instances, they're gone. And everything's based on Docker containers or Amazon machine images. And so just for fun, I did another one yesterday. So this is in Peru. This is kind of a famous area in Peru of deforestation for gold mining. So they're deforesting to mine gold in these areas. And you can actually see, when I mentioned earlier that there would be cloudy images, as you watch the sequence of images, you'll see little dark patches come in here and there. Those are actually areas of increased tropospheric water vapor. But over time, and this is starting in 2016 to the current, you can see the development of a fair number of the deforestation rather of a large area here. And then if we take the same data set and run it through our change detection algorithm, we can see that most of the forest, thankfully, isn't changing. In fact, most of the forest is staying constant. Gray in this case would indicate no change. But if we zoom into that area, we can very clearly see those areas that are being deforested. Those areas that do have change, we can see some change along the rivers as well, things like that, sandbars moving around and whatnot. But again, this is an automated product. This is something that I didn't touch, something that I didn't really do anything with other than grab a little crop out to put in this presentation. So where are we going? We really want to work with you all, with the optical community, to try to make a product that actually is usable in the workflows that you use and that you have. That comes down to formats, comes down to metadata, consistent metadata across products, things that you can understand so that make sure that you can use the product that we provide you. My holy grail is I'd love to see people doing actual analysis in their browser. We actually we currently are looking at geotiff.io for this, but now I think we're going to look at the EO browser toolkit that was displayed yesterday. That looks like a great product. Provide the data, throw it into a bucket. People can come in and create publication-ready charts. They can export in whatever format they want. If they want an Excel spreadsheet, they can export an Excel spreadsheet. That's kind of the goal for us. Hopefully maybe we do the processing, maybe you do it. We're actually taking that whole HYPE system and we're making what we call HYPE in a box, which is just a bunch of CloudFormation templates where you can go out and you could spawn that out in your own Amazon account. You'd have all the processing scripts, all of the open source software. The only thing you wouldn't have you wouldn't have any of the proprietary software, but we do provide all of the proprietary software scripts. So if you have Gamma Remote Sensing Toolbox or something like that, you can install it yourself and run using our scripts. So that's where we're headed, and thank you. And if anybody's been wondering why there's a 13-year-old playing Fortnite in the background, or in the back of the room, my son and I went to Utah last week, and we're hiking across southeast Utah, and so he was tagging along for this trip. So thank you very much.
Thank you.
Testing out this other microphone. Whoa, it's live. It works. Thank you, Scott. If Peter and Gina want to come up here too, and we can have our panel discussion too. And Gina, I'll give you this, since we only had 2 of the other microphones, in case you have questions. Make sure this one's on. Yep, this one's on. So, any questions for our panel? Here we go. Chandler?
Yeah, this question's for Gina. So maybe you can just tell me if I understand this right, sort of the difference between what you and Arind's different approaches were. He was trying to normalize NDVIs using normalization based on the sensor, sort of this intrinsic data. And do I understand that in your case, it's more about each individual scene, like you'd look at it and then you'd compare it to a crossover and then you'd like normalize them all every time you wanted data, or is that like to make a calibration that you could apply later to non-crossovers? Does that make sense? Like, are you, okay, to utilize your technique, would you always need a crossover and then you'd be like, oh, now I can normalize this whole ARD stack? Or is the purpose to build some sort of model that you can then use all the time to convert any PlanetScope scene to Sentinel?
Is this on? Okay, yeah. Yeah, I mean, ideally, you would just be like, sorry, can you repeat the first thing that you said?
Yeah, is the goal of this to create a model that then you apply to scenes where you don't have crossovers? Like you could have some sort of model that always works from PlanetScope to Sentinel, or is this like always the case where you have the full ARD stack for every scene?
Yeah, I mean, that should be one sort of implementation where it's like you've trained the model on just like that specific scene using a stack of data from like before, and then so ideally you could apply that to a scene where you don't have a crossover. So like in the case where you've hypothetically found the relationship between like PlanetScope and Sentinel-2 using those crossovers, then you have sort of like a new PlanetScope scene like without a Sentinel-2 crossover, and then the idea is that you can produce a Sentinel-2 like PlanetScope scene for that specific day.
Okay.
Yeah.
Just to follow on to that question, do you have any idea of how quickly the machine learned calibration falls off in terms of geography or in time? Right? So if you, the next image that the PlanetScope takes, if you were to run the previous model through to calibrate that to Sentinel or vice versa, do you have any idea how those deviations trend relative to the more traditional sensor-based calibration approach that sort of is supposed to work extensively?
Right. That's actually something I haven't been able to test. Just like, I mean, the only thing I've tested is looking at the different parcels, but I haven't really looked, I guess, throughout time. Yeah.
Maybe it would help if you clarify what kind of tests you've done. Like, have you tested data looking forward or looking backwards or missing data in the middle? It would be interesting to know.
Sorry, when you say testing data, you mean like looking at the image that I'm trying to predict for the prediction day?
Right. And did you train it using a data set with future and past data, or did you?
Yeah, so at least with the analysis I performed, it was just like, so for example, if I had like 5 different crossovers, I was only training, so the date I would predict on would be sort of in the middle. So I trained on data from before and after, but not like exclusively from past data or future data.
I have a question for Scott. So in-SAR analysis is typically something that runs for quite a while before you get something out of it. Could you estimate what your, I don't know, per square kilometer processing time for a given, I don't know, set of tens of images or length of time series is?
I can't right off the top of my head. I mean, we typically, so a lot of times you have to process full Sentinel frames at this point. A full Sentinel frame, in-SAR processed and phase unwrapped, typically runs in less than an hour. Phase unwrapping is kind of a black art though, and so it can vary greatly, and you have to be able to detect that and kill it before it's done. When we do our time series though, we typically do one cycle variation and 2 cycle variations. So for a given master, we go back and forth, 1 cycle and
so
2
that's
cycles.
1 hour for 2 images and 2 hours for 3 images, or?
Yeah, that would be
Something
fair.
like- Yeah, okay,
Yeah, yeah.
thanks.
And that, like I said, that varies greatly depending on how fast the phase unwrapping takes.
Hey, Scott.
Yes, sir.
My question's more on maybe kind of riffing on that a little bit, and it's more about thinking about interferometric products as a not a on-demand kind of product, as more of a, we're doing this on a regular cadence. Have you given some thought to producing this at, say, regular cycles and having that already ready to go, rather than I do this on demand, and can I bring that into sort of operational flows without having to suffer that hours and hours of compute and everything else?
So for certain areas, that's exactly what we're doing. I mean, doing in-SAR time series for the world is kind of tough. But we have a number of sites that we do process actually regularly. We have some users right now that are using our system to generate new interferograms every time a new data product comes in line. Then they take that in-SAR time series that they already have. They basically add one more to it and do a SBAS inversion or something like that. But in general, what we do, it's a little difficult depending on how you're processing. If you're processing to a single master image or something like that, then there can be times where you have to reprocess the whole stack. But in general, we try to keep the stack intact so that as new imagery comes in, we just add a new interferogram to the stack, one more piece of the time series. There's a little bit of trickery that happens from time to time as processor versions change and things like that, where we have to go back and repeat processings. But in general, we try to maintain the stack on disk so that we can just add to that stack for the areas that are operationally important.
Very cool. Do you have a process where one can propose study sites, research sites, or operational sites for where I would love to see that stack being built, and then we can start to look at things like differential in SAR and all the other coherent change detection, all the other wonderful things that one can do with interferometry?
Yeah, I mean, if you actually go into the system and then email me, just let me know when you try to, because we have to approve users still, kind of one at a time there. But yeah, we could generate a time series for really anywhere that you're interested in. We have a couple of users that we have one NASA-funded project right now called SAR Views, which is looking at natural hazard sites, so volcanic and earthquake areas around the world, where we're doing kind of continuous monitoring in general of volcanic hazards for the most part, but also some earthquake sites. And so something like SAR Views, this kind of equivalent to something like SAR Views, just setting up a new area and saying, okay, we're gonna monitor this area now.
Thank you.
I have a question for Gina, is it?
Yeah.
Why did you decide to use regression trees rather than just linear regression, such as other people have been using? Have you tried one and it didn't work out, and that's why you decided to use a more heavy machine learning approach?
Yeah, good question. I didn't necessarily experiment with different methods, but since the idea was sort of just to analyze a local area, I assumed, it would be okay to sort of overfit the model to the data. And then the idea is that you build a new model for each different scene that you're looking at or area. So I guess there's not really a straightforward answer to that. But I also read Dr. Hoberg's paper too, and noticed that the SESTEM implementation was based on a model tree regression. So I figured maybe stemming from that inspiration to look at a random forest regression.
Okay, I think we have one more question. Oh, we have plenty of time, so.
So Gina, so you're saying your correction is constant in time, or do you make, for each scene, would you make a different type of correction, a different model?
Yeah, it's a really good question. I actually haven't necessarily tried doing that. My guess is that if you were to make a new model for every scene, one, you would need a crossover for that, and then two, actually I lost my train of thought there, but yeah, I mean, I haven't tried necessarily.
So I guess it doesn't really correct for if you have fluctuations in the radiometric quality of each sensor. It wouldn't correct for that, would it? If you use the same reference data to kind of, if you apply the same model to the same 5 scenes in a time series, maybe.
Mm-hmm.
So it wouldn't really correct for the fluctuations you might see.
My guess is probably not.
Yeah, right. Okay, good.
Hello, I have a quick question related to the SAR data sets that you use. One of the things that Stephen presented on was the family of specifications for the ARD, and we have the radar backscatter ARD in place. Have you looked at that and with your use of multiple data sets, looked at that and thought about how the ARD might be used or might be better?
This is a Card4L for radar. We actually have looked at it, and it's something we're taking into account, or we're trying to meet if we can. We actually have our sponsor, the sponsor of our data center is NASA, and NASA is actually interested in supporting Card4L. And so if there is a way that we can push that forward with our products, we will be attempting to do so. I don't know for sure yet. I can't tell you for sure that everything is in there that we want, or that there aren't things that are missing, but that is the intent at this point.
Cool, thank you.
For Peter, the 3-component land surface model that you have looks really interesting, but it also looks very simple. So and it looks specific to Australia. Did you see any regional variation in its usefulness? So is there a particular specific type of climate or vegetation where this kind of unmixing works and where this kind of unmixing doesn't work within Australia? Because Australia is still quite a big country.
Yeah, it depends. I think we're getting reasonably good calibration. So now when we go into the field, I basically have a couple of maps on my phone. One, a map of spectral distance of, from where we've sampled before, and spectral angle. But just from looking at the areas and how they work, like there's a few problems. One, really bright areas cause problems. So when you're sitting up, Landsat 5, when you get saturation, basically everything goes away because you're right on that level of signal to noise. And really bright soils, dry grass and bright soil look really similar, and it's really hard to split the two. And sometimes the model will just flop over and go, it's 100% dry grass rather than 100% bare. And also in dark soils, although I think we're doing better there than elsewhere. So in dark soils, you can have a problem, but then there's a lot of people operationally using that model now and looking at the time series drop in bare ground to map burnt areas. So I think that's working pretty well. So I think it's just the bright areas there where we have quite a few problems. But I think we might be doing better now as we move to a support vector machine based model based on that. I think that's allowing a bit more flexibility than the n-member based model that we had before.
All right, so do you think there would be a possibility to develop a global land cover vectors that could combine your model with what we've seen from Vito, I think, for Africa, where they had greenness, wetness, and bare land and
Yeah.
similar thing.
Yeah, I mean, it's because it's their biophysical rather than the tasseled cap outputs. I think so. Like so GeoGlam applies the same set of data to MODIS and applies it globally, and it looks all right. And I think and that was using an earlier data set that only had 1,000 sample sites rather than all the extra sites we've now got across the savannah in Central Australia. So I think there's good opportunity to do that. The data set itself is pretty much out in the open. At least 3,000 of the data points are, and we're working on getting the other ones out there. There's a few points that were sort of captured by jumping over the fence without getting permission from landholders, and just got to wait. You know, I think once enough time passes, you can publish that stuff, and you're okay. So when we get there, that'll do it. But yeah, and then it should be pretty easy to apply. You know, in a Lambda function or anything. So.
All right, if there are no other questions, just thank the panel for your insights there. Before we take a break, I think Ignacio has a little bit of an announcement for some feedback we'll be soliciting from everybody, and then we'll conclude. I think we have one more session starting at 3:30. So.
So let me see. So we have one more session, and then we have a slot for one last panel for discussion. And one of the things I wanted to do is to use these 20 minutes we have until 3:30 I want to show you guys the beginning of the survey I'm about to send you, and I'll send it to you. So if you guys want to use those minutes to sit down and jot some thoughts about next steps, that will be a great opportunity while you get some coffee. The other is if anyone has a strong input on the topic for the last panel. One of the topics we had, two topics that I had in mind to close the evening were operational interoperability, and by that I mean a question we haven't touched on that I wanted to invite or get a few people self-nominated to discuss, which is latency times when you need to do data fusion. A lot of things need to be interoperable, but the products need to be published and ready at the same time, so you can publish near real-time data fusion products. There's a few of you guys who know who you are, who understand the systems engineering portion of this. The other topic is ingestion of public data sets into the cloud. We have 2 or 3 people here whose part of your main responsibility is actually maintaining and owning the ingestion into the Google Cloud and AWS of Sentinel and Landsat, and having a couple of you guys to come to the front and discuss a little bit about standardizing and open sourcing ingestors and just a general sense of how that interacts with latency. So that's kind of the topic I had to close, which we didn't really zoom into, which is actually a practical blocker for those of us who publish data fusion products we have to surmount every day. So that's a topic. If you agree or disagree, please grab me now. We can discuss. This is open. This is our meeting. And let me pull up the questions I have for the survey. What I'm going to do is I'll go through it, and I'll be here for a few minutes, and if I don't hear major objections, I'm just going to send it to you guys. So let me see. Also, if you have a chance to send us, to respond to the email thread about the presentations, we're taping all the presentations. We're going to probably create a YouTube channel, so we're going to slice them, edit them, and post them. If for any reason you think your presentation should not be posted in the YouTube channel, let me know, but we're going to do that, and I'll try to we'll set up a web page with the actual PDFs of the presentations. And it will be really nice for the sake of completeness, so we can all digest what has just happened in this meeting. If we could really have all the presentations, I have about a third to a half right now. So again, this will be a good moment to do that. All right, let me see what's going on with the screen. Cool. No, no dinner. Let me see. Just 1 second. All right, so this is what I have. I'm going to send the form right now that is essentially asking for literally your name, affiliation, email, industry, and then a few questions. Feel free to skip, questions that you feel are not relevant, but I'm really going to ask you guys about what do you learn in the workshop, what is the take-home message, any immediate actions they will take to contribute to interoperability in your everyday job, any action items you take to your own roadmaps based on what you learned here. We're asking you guys if you, what's the main blocker to interoperability? I think we had general agreement on what are the things that work, but it would be nice for all of us to prioritize the things that don't work in the next few months to collaborate. Do you own or maintain any piece of interoperability infrastructure, like ingestors, algorithms, services, or any open source software? We wouldn't really capture that, so we can set up some working groups. What do you think of the workshop itself? And would you join us if we do a sidecar meeting at ASPRS next April? So that's a practical question in Denver. If not, we're open to different countries or other locations, proposals, times. I think a good option would be just meeting in Denver in April again. And yeah, if there's anything we can do better. So I'm going to send this out in about 2 or 3 minutes. Please come to the podium and suggest any questions, or if there's anything that sticks out as missing or redundant, just speak. Let me know. ASPRS, who can describe ASPRS here better than me? Who is a veteran SPRS organizer? John, maybe? Yeah. No, yes, Denver, Colorado, I think, yeah. So Denver, Colorado, April. I don't know the exact date off the top of my head, but now submissions is where this is when we should be submitting papers if we attend the conference, but we could do a sidecar meeting for a couple of days, ideally co-located. So I'm going to try to get us a venue in the same place where SPRS is happening. It's a great conference. So American Society for Photogrammetry and Remote Sensing. And I think the general idea, I mean, this is an interesting conversation to have. I was thinking if this was useful and a nice group of people, meet again at ASPRS, and then 9 months later, meet again at AGU of 2019. So keep it moving fast. And ideally, this was a little bit of a survey meeting. Let's move on to some actions and discuss some homework in the next month. So when we meet, we made some progress, and or at least capture what has been done already. Does that make sense? Greg?
Yeah, the ASPRS is tied together with the International LiDAR Mapping Forum. It's in Denver. I can't remember if, I think it's the first week of, last week of January, last week of January in Denver. I know ASPRS has been going through their process to establish meeting sessions, joint sessions, and approving the abstracts. And I guess John Christofferson is the upcoming Primary Data Acquisition Division Chair at ASPRS, so maybe he can help set something up.
Do you guys think that would be a good place to meet up again? Should we meet up again? Closer to what? Sorry. Yeah, good skin is gonna be. Oh, it's gonna be beautiful. I mean, I think it can be amazing. Yes, we could consider. I mean, eventually we could consider something in Europe. I mean, that's pretty realistic. I think. Mm-hmm. Yeah, I mean that makes total sense. It all boils down to logistics. This is a very cheap event. We have to do it under low cost and be in places where we can secure a venue and have a good critical mass of people already in town, so we can reduce, travel expenses and things like that. I think we're all definitely open to meeting on the East Coast. It boils down to maybe someone at NASA Goddard in DC, can provide an auditorium or a place like that, or USGS as well. We've done JC there, so it all boils down to really having the venue in a place where we can all get together. So I think DC is another good location. Yes, South Dakota, that's another good location too. Yeah, I mean this is a really important conversation. So I mean, if we believe we should keep talking about this and have an interoperability centric type of venue, and should be doing at least this 1 or 2 more times and see where it goes. I think having a kind of a place that is exciting for us to go to and convenient is important. So if anyone has concrete, opinions, especially on the European side, I mean, we have offices in Berlin. We could try to use them to host if it's a small meeting in our Berlin office, but maybe someone like DLR or we can do it in Rome, yeah, in the Phi Lab, or yeah. Ideally, a place that is convenient, yeah, Paris or close to Brussels. All that area is very reachable from Europe, and it's cheap to fly from here. So, yeah. Which one? Oh yeah, but it's too soon. That's the problem. Yeah. Oh, sure. I think yeah, we have SPIE, and also we have IIC, which I've never been to, but happens a little bit later, but might be a bit more aerospace-y. The EGU, Vienna. Well, we need someone that can hook us up with a free venue, essentially, right? This is not so. If you know anyone, I love Vienna. I mean, you should do it. I would say. Yeah. Well. One of the what offices, sorry? Oh, okay. Well, look, I'm going to add a new question to the survey. That is suggested locations. If I don't hear, we can arrange things in the U.S. and in the western kind of center mountain area. That's where we have most of our, connections. But if somebody wants to volunteer, if we do it there, then we'll really need to co-chair it and have someone local help us organize it. We want to keep the momentum, and so if we don't hear a strong alternative, we might still base it in maybe the center of the U.S., or if we can find something in this coast, if that's okay. But the idea is to have a cadence closer to kind of open source software development, start moving fast rather than meet once a year and go through a lot of talks. Ideally, we'll be more hands-on next time. So, yeah. Yes. Yeah, we have an email list already created in Google Groups. It's kind of temporary for this particular event. I love the idea of Slack. Yeah, we can set up a bunch of social media things so we can talk. But we have at least an email list that we've been using right now, and I'm sure there is existing ways to talk. We don't have to reinvent the wheel. So maybe I'll add 2 questions: suggested locations, suggested way of communicating. So maybe we can get behind something that already exists rather than spinning up one more anything, right? Okay. I'm gonna get to work and add those 2 questions. Is there anything else you guys wanna capture from the rest of the audience? Because I'm gonna share the results of this with everybody. I'll write them up as a summary as well. Yeah.
Just a comment. I think there's maybe some key. Susan just mentioned this to me, and I think maybe it's a key thing that there may be some ad hoc working groups of specific users or people that are working on common things related to ARD and interoperability that you may want to establish, like you said, a Google group, and then have some telecons or ad hoc groups that are pushing some of those things forward. So that might be something that you want to say, are there some key ad hoc things or working groups that we should start?
Yeah, I think this is a fantastic idea. We have a patchwork of, at least at Planet, of engineering sync kind of meetings with customers and also players in the in the government sector. So maybe one follow-up item, as you suggest, is maybe every other month we do a 3-hour-long video conferences with a couple of talks and updates on things as they come through. And I love that idea. This is something we do in a disorganized fashion already with a lot of our customers, and none of this is really secret work, so we're doing this in the open, really. So having an engineering sync type of, maybe an hour and a half call where we have a couple of presentations and whoever is available to join can join, that will be good. Does that sound like a good idea? I see some nodding, so I'll say yes, it's a good idea to some. So, cool. All right, so we have let's get some coffee. We have about 5 minutes left. I'm going to send this out right now, and come grab me if you have any suggestions. Thank you.